A post from Discord.code from their blog, their engineering tech blog. How Discord stores trillions of messages. So if you remember, we had a couple of videos ago where I read the blog post, the great blog post from Discord on how they managed billions of rows from 2017, where they moved from MongoDB, which was good for them because of the simplicity, its flexibility, to Cassandra, to billions of messages, to storing billions of messages, and they use them actually to store and retrieve them. Actually, to store all messages and to actually retrieve all messages that they need. But now they move to trillions of messages. So now the question is whether they would stay with Cassandra, move to another database. We need to remember also that Cassandra is written in Java, so it has the GCs, of course, some frees. Also, we need to remember that in Cassandra, it's optimized for writes. So writes should be something like less than 1 millisecond or sub-millisecond or around this, or up to 5 milliseconds. And reads could be on the tens of milliseconds or 5 milliseconds and above, of course, depending on your traffic. Right, or it could be 5 milliseconds and above, while writes is up to 5 milliseconds. Okay, so let's continue with this. So how Discord moved to store trillions of messages, and this was written recently in 2023 by Bo Ingram. So they say this. In 2017, we wrote a blog post on how we store billions of messages, and I have this couple of videos ago. We shared our journey of how we started out using MongoDB but migrated our data to Cassandra because we were looking for a database that was scalable, fault tolerant, and relatively low maintenance. We knew we'd be growing, and we did. We wanted a database that grew alongside us, but hopefully its maintenance needs wouldn't go alongside our storage needs. Unfortunately, we found that not to be the case. Our Cassandra cluster exhibited serious performance issues that required increasing amounts of effort just to maintain, not to improve. Almost 6 years later, we've changed a lot, and how we store messages has changed as well. Our Cassandra troubles. We stored our messages in a database called Cassandra Messages. As its name suggests, it ran Cassandra and it stored messages. In 2017, we ran 12 Cassandra nodes storing billions of messages. At the beginning of 2022, we had 177 nodes with trillions of messages. To our charging, it was high-toil system. Our on-call team was frequently paged for issues with the database. Latencies was unpredictable, and we were having to cut down on maintenance operations that became too expensive to run. What was causing these issues? First, let's take a look at a message. So this is a message that Discord stores. So they have the channel ID, they have the bucket ID, they have the message ID, the auto ID, the content. Bucket ID is something that they would assign to a message, to a couple of messages, and their primary key is a composed one out of channel ID, its bucket ID, and the message ID also. Ordered by message ID descending. So newer messages would come newer in this database because I think message ID in their case was ordered. The CQL statement above is a minimal version of our message schema. Every ID we use is a snowflake, and I will refer to what they mean here by snowflake in a future video post, making it chronologically sortable. We partition, so you see the ID of the message ID, it's both an ID, but it's also chronologically sortable. You can do this by concatenating a date to some random ID even. We partition our messages by the channel they're sent in along with a bucket, which is a static time window. This partitioning means that in Cassandra, all messages for a given channel and bucket will be stored together and replicated across 3 nodes, or whatever you set in the replication factor. Within this partition lies a potential performance pitfall. A server with just a small group of friends tends to send order of magnitude fewer messages than a server with hundreds of thousands of people. In Cassandra, reads are more expensive than writes. Writes are appended to a commit log and written to an in-memory structure called memtable that is eventually flushed to disk. Reads, however, need to query the memtable and potentially multiple SS tables on disk files, a more expensive operation. Lots of concurrent reads as users interact with servers can hotspot partition. So if you have a lot of concurrent reads, for example, someone publishes messages, then many users come and try to read this message, you will have a hotspot, which we refer to imaginatively as hot partition. The size of our dataset when combined with these access patterns led struggles for our cluster. When we encountered a hot partition, it frequently affected latency across our entire database cluster. One channel and bucket pair received a large amount of traffic, and latency in the node would increase as the node tried harder and harder to serve traffic. So the latency in the node is increasing because then this node is a hot partition and it needs to serve more and more clients to serve traffic and fell further and further behind. Other queries to this node were affected as the node couldn't keep up. Since we perform reads and writes with quorum consistency level, all queries to the nodes that serves the hot partition suffer latency increases, resulting in broader end-user impact. Cluster maintenance tasks also frequently cause trouble. We were prone to falling behind on compactions, where Cassandra would compact SS tables on disk. So if you remember, they have commit log in memory and then they have SS tables on disk, and then you still need to compact all these SS tables. Like fragmentation, if you remember, from Windows disks machines. On disk for more performant reads. Not only were our reads then more expensive, but we'd also see cascading latency as a node tries to compact. We frequently performed an operation we call the gossip dance, where we'd take a node out of rotation to let it compact without taking traffic. Bring it back in to pick up hints from Cassandra's hinted handoff, and then repeat until the compaction backlog was empty. So this is really heavy. You need to take out a node, compact it and return it. It's a hinted handoff, meaning it's beginning to serve again. Not easy. And this sounds manual, as they say. We also spent large amount of time tuning the JVM's garbage collector and heap settings because GC pauses would cause significant latency spikes. Changing our architecture. Our messages cluster wasn't our only Cassandra database. We had several other clusters and each exhibited similar, though perhaps not as severe faults. In our previous iteration of this post, we mentioned being intrigued by ScyllaDB a Cassandra compatible database, so this should be compatible with Cassandra, but it's written with C++, so it should have garbage collector free life, faster repairs, stronger workloads isolation, V8 shard per core architecture, and garbage collector sounded quite appealing. So as it looks, they are going to move to this database. So Mongo to Cassandra to now ScalaDB. Although ScalaDB is most definitely not void of issues, it is void of a garbage collector, since it's written in C++ rather than Java. Historically, our team has, and I wonder if today there is something in Rust similar to this. Historically, our team has had many issues with the garbage collector on Cassandra, from GC pauses affecting latency all the way to super long consecutive GC pauses that got so back that an operator would have to manually reboot and babysit the node in question back to health. These issues were a huge source of on-call toil and the root of many stability issues within our messages cluster. After experimenting with ScalaDB, and observing improvements in testing, we made a decision to migrate all of our databases, while this decision could be a blog post in itself. The short version is that by 2020 we had migrated every database but one to ScalaDB. The last one, our friend Cassandra Messages. Why hadn't we migrated it yet? To start with, it's a big cluster with trillions of messages, so it already contains trillions of messages and nearly 200 nodes. Any migration was going to be involved effort. Additionally, we wanted to make sure our new database could be the best it could be as we worked to tune its performance. We also wanted to gain more experience with the ScalaDB in production, using it in anger and learning its pitfalls. We also worked on to improve ScalaDB performance for our use cases. In our testing, we discovered that the performance of reverse queries was inefficient for our needs. We execute a reverse query when we attempt a database scan in the opposite order of the table sorting, such as when we scan messages in ascending order. So because it's messages, so the latest messages are the most important. This is why they had the order by descending. The ScalaDB team prioritized improvements and implemented a performant reverse queries, removing the last database blocker in our migration plan. We were suspicious that slapping a new database on our system wasn't going to make everything magically better. Hot partitions can still be a thing in ScalaDB, and so we also wanted to invest in improving our systems upstream of the database to help shield and facilitate better database performance. So solving the GC is going to solve these poses, but what about the hot partitions that I said? Because also with ScalaDB, we are going to have hot partitions, because if a message is going to be read from so many clients, this would still be the case in ScalaDB, so we need a solution for this. Data services serving data. With Cassandra, we struggled with hot partitions. High traffic to a given partition resulted in unbounded concurrency, leading to cascading latency in which subsequent queries would continue to grow in latency. If we could control the amount of concurrent traffic to hot partitions, we could protect the database from being overwhelmed. To accomplish these tasks, we wrote what we refer to as data services. Intermediary service that sits between our API monolith and our database clusters. When writing our data services, we chose a language we've been using more and more at Discord, Rust. We'd used it for a few projects previously and it lived up to the hype. For us, it gave us a fast C++ speeds without having to sacrifice safety. Rust touts fearless concurrency as one of its main benefits. The language should make it easy to write safe concurrent code. Its libraries also were a great match for what we were intending to accomplish. The Tokio ecosystem is a tremendous foundation for building a system on asynchronous I/O, and the language has driver support for both Cassandra and SkyliDB. Additionally, we found it a joy to code in with the help of the compiler gives you, the clarity of the error messages, the language constructs, and its emphasis on safety. We became quite fond of how, once it compiled, it generally works. Most importantly, however, it lets us say we rewrote it in Rust. Memcred is very important. Yeah. So basically, if I'm willing to take the toll of GC, I'm personally perfectly happy with Java. If I can't stand the GCs, if I'm developing a database, something that cannot stand the GC, right? Then I would need another language, be it C++, C, or today Rust, if I don't want GCs. If I'm okay with GCs, Java could be the solution for me. I'm a Java guy. Okay, our data services sit between, of course you could do it in Go, Lang, of course you could do things in Python, but really it depends to what is the core language that you decide to use, the core backend language. My claim is that if you're willing to take the toll of GC, then Java is usually the perfect language for you. Right? This is my claim, and I'm saying this from someone who has written code in Go, in Scala, in Java, in Python, in Ruby. I wrote some code, some little Perl. In Rust, I admit that I didn't use Rust, but I would choose Rust in cases I would need a C++ replacement. In those cases would be when I really need something fast and I cannot take GC as an excuse. Our data services sit between the API and our ScalaDB clusters. They contain roughly one gRPC endpoint per database query and intentionally contain no business logic. The big feature our data services provide is request coalescing. If multiple users are requesting the same row at the same time, we'll only query the database once. The first user that makes a request causes a worker task to spin up in the service. Subsequent requests will check for the existence of that task and subscribe to it. So everything in computers that there is this claim that everything can be solved with another layer of abstraction. So this is what they are doing here. They're building another layer of abstraction in between the database and the clients. That worker task will query the database and return the row to all the subscribers. This is the power of Rust in action. It made it easy to write safe concurrent code. So we see here that we have here some requests coming in. So we have one request, we have a second request, but note that they all ask for message 456. So because they have here the service, this intermediate service worker or whatever they call it, then it can remember, and while it's doing this round trip to the database, it needs to do only one because all of this is asking for the same message, 456. So it would serve them all, single request to database. If they come at the same time, of course. Let's imagine a big announcement, and they said they had this problem. They had this problem, which they describe exactly here, the hot partition. Let's imagine a big announcement on a large server that notifies everyone, users, are going to open the app and read a message, sending tons of traffic to the database. Previously, this might lead to a hot partition, and on-call would potentially need to be paged to help the system recover. With our data services, we're able to significantly reduce traffic spikes against the database. The second part of the magic here is upstream of our data services. We implemented consistent hash-based routing to our data services to enable more effective query scheme. Now the question is which data service does your call, because now you have multiple databases and you have multiple data services that call the database, but you want all these that call for row 56 to have to the same data service. So you need also to control this route from clients to data services. For each request to our data service, we provide a routing key. For messages, this is a channel ID, so all requests for the same channel go to the same instance of the service. This routing further helps reduce the load in our database. Okay, so now what I show here is that they have some clients that calls, and you see that channel 3 goes to data service 3, channel 2 goes to data service 2, channel 4 and 1 are going to message service 1. So they show how they do like the load balancing for which channels go to which service. These improvements help a lot, but they don't solve all of the problems. We are still seeing hot partitions and increased latency on our Cassandra cluster, just not quite as frequently. It buys us some time so that we can prepare our new optimal SkylaDB cluster and execute the migration. A very big migration. Our requirements for our migration are quite straightforward. We need to migrate trillions of messages with no downtime. And we need to do it quickly because while the Cassandra situation has somewhat improved, we're frequently firefighting. Step 1 is easy. We provision a new SkylaDB cluster using our SuperDisk storage topology. By using local SSD for speed and leveraging RAID to mirror our data to a persistent disk, we get the speed of attached local disks. And I'll go over this post again, also over what this code will describe as the speed of local disks. SuperDisk storage topology. I'll go over this in future posts. With our clusters stood up, we can begin migrating data into it. Our first draft of our migration plan was designed to get value quickly. We'd start using our shiny new SkylaDB cluster for newer data using a cutover time, and then migrate historical data behind it. It adds more complexity, but what every large project needs is additional complexity, right? We begin dual writing new data to Cassandra and SkylaDB and concurrently begin to provision SkylaDB Spark Migrator. It requires a lot of tuning, and once we get it set up, we have an estimated time to completion, 3 months. Ooh. So what they found here is that if they let their migrator run, it would take like 3 months to migrate everything. That time frame doesn't make us feel warm and fuzzy inside, because it needs to read all the rows from the older Cassandra to the new Skyla and write them. And we'd prefer to get value faster. We sit down as a team and brainstorm ways we can speed things up until we remember that we've written a fast and performant database library that we could potentially extend. We elect to engage in some mem-driven engineering, I like his style, and rewrite the data migrator in Rust. In an afternoon, we extended our data service library to perform large-scale data migrations. It reads token ranges from a database, checkpoints them locally via SQLite, and then fire hoses them to SkylarDB. We hook up our new and improved migrator and get a new estimate. 9 days. So instead of 3 months, 9 days. If we can migrate data this quickly, then we can forget our complicated time-based approach and instead flip the switch for everything at once. We turn it on and leave it running, migrating messages at speeds of up to 3.2 million per second. Several days later, we gather to watch it hit 100% and we realize that it's stuck at 99.9999. Maybe it's stuck on reads complete. No, really. Our migrator is timing out reading the last few token ranges of a data because they contain gigantic ranges of timestamps. So if you remember from our previous post on Cassandra, we said that Cassandra is not actually deleting at the moment you ask to delete something. It's writing a marker on it that it should be deleted. But what happens if you have a node where 99% of it is marked as deleted and you need to scan it? That were never compacted and it's not going to be compacted. The way in Cassandra, only after some time it would remove it. We compact that token range and seconds later the migration is complete. We performed automated data validation by sending a small percentage of reads to both databases and comparing results. And everything looks great. The cluster held up well with full production traffic, whereas Cassandra was suffering increasingly frequent latency issues. We gathered together at our team on site, flipped the switch to make SkylarDB the primary database, and ate celebratory cake. Several months later, we switched our messages database over in May 2022, but how it held up since then? Very important question. Sometimes posts end up with, we did this and now it's working. What afterwards? It's been a quite well-behaved database. It's okay to say this because I'm not on call this week. We are not having weekend-long firefights, already better. Nor are we juggling nodes in the cluster to attempt to preserve uptime. It's a much more efficient database. We are going from running 177 Cassandra nodes up to just 72 SkylarDB nodes. SkylarDB nodes has 9 terabyte of disk space, up from average of 4 terabyte Cassandra nodes. I take it they say here that the increase into 9 terabyte is the ability of single SkylarDB node to have a bigger disks rather than we use the SkylarDB integration and we increase the disk size because they could also increase on the Cassandra. So they didn't say this explicitly, but this could mean that the SkylarDB node handles more data. Otherwise, they would increase the Cassandra node DBs, right? Local disks. Not clearly stated, but probably. Our tail latencies have improved drastically. For example, fetching historical messages had a P99 of between 40 to 105 messages on Cassandra. So read was about, let's say, 70 milliseconds here, P99. With SkylarDB having a nice chill 15 milliseconds, which is great P99 latency. And messages insert performance going from 5 to 70 milliseconds on Cassandra to steady 5 milliseconds on SkylarDB, thanks to the aforementioned performance improvement. Yeah. Thanks to the aforementioned performance improvement, we've unlocked new product use cases now that we have confidence in our message database. At the end of 2022, people all over the world tuned in to watch the World Cup. One thing we discovered very quickly was that goals scored showed up in our monitoring graphs. This was very cool because not only is it neat to see real-time world events show up in your systems, but this gave our team an excuse to watch soccer. during meetings. We weren't watching soccer during meetings, we were proactively monitoring our system performance. This is goal score 1, goal score 2, goal score 3, etc. We can actually tell the story of the World Cup final via our message sent graphs. The match was tremendous. Lionel Messi was trying to check off the last accomplishment in his career and cement his claim to being the greatest of all times and lead Argentina to the championship, but in his way stood massively talented Kylian Mbappe and France. Each of the 9 spikes in the graph represent an event in the match. Okay, so we have goals in the match that we see them. And these are in general the messages per second. Yeah. People all over the world are stressed watching this incredible match, but meanwhile Discord and the messages database aren't breaking a sweat. We are way up on messages sent and handling it perfectly with our Rust-based data services and ScalaDB. We're able to shoulder this traffic and provide platform for our users to communicate. We've built system that can handle trillions of messages, and if this work is something that excites you, check our career page. By the way, they didn't fully mention if the communication, right, if the communication from client to their service, if this is the client, to be it SkylaDB / Cassandra. So how much time this took in milliseconds and how much time this took in milliseconds. Right, because it's a service to service, we can assume probably that this is going to be less than 1 millisecond, right? Even less. But it's possible. It really depends on the size of the message. But I wish they would specify how much this took, how much this took, and how much this took. We know that this can take for writes like 5 milliseconds and less, and this should take, I mean, at most. And this they said they got to with SkylaDB to 550 milliseconds. And I wonder how much is this. Maybe we see it. Probably not that much if they didn't specify it. Okay. So with that, we have arrived to the how Discord moved from billions of messages into trillions of messages from 2023, which is pretty recently. And what I would like to say is that there were 2 parts to this, right? One was moving from Cassandra to SkylaDB, mainly to eliminate GCs. This is C++. This was probably Java, right? So mainly to eliminate GCs, and also they added some intermediary service such that because this would still not solve hot partitions. In order to solve hot partitions, it's kind of cache, it's not exactly cache. It's a bunch of calls coming into the service. They bundle them, they make a single call and then a single result. And imagine you have here 1K. So you just saved 1K request to the SkylaDB. Okay. So this was Discord, how they moved to